Hi, my name's Liz Rice, and welcome to eCHO episode 119 of the eBPF and Cilium Office Hours live stream. As always, if you're watching us live, we'd love to hear where you're watching us from, so drop us a comment and say hello. This is going to be the last eCHO episode of the year. Hi already to Anais. Good to see you there. Let's bring up the headlines. Just have a couple of things I wanted to share before we get into the main topic of today. So, this is the last show before the holidays and before the new year. I've got one blog post that caught my eye that I thought might be really interesting to the eBPF fans amongst us. As always, I've scrolled to the bottom rather than showing you the title. So here we go. It's about eBPF networking techniques by Luis de Losa. Really interesting details about different points you can attach eBPF programs and how you can use eBPF to redirect packets. So that's a really great resource if you're interested in networking with eBPF. Another thing I want to show you today, and all the links are in the show notes, which are, no, that side. I'll get it right eventually. On HackMD, you'll find the show notes, and you will find in there links to everything I'm showing you, including a sneak preview of the 2023 Cilium annual report. So this is just highlights of what's happened on the Cilium project during the year. The big thing really was graduation, but there's a whole bunch of statistics and interesting tidbits about what's been going on in the Cilium project during this year. So yeah, you can find that on GitHub. And the last thing, since we are approaching the holiday season, I know Duffy showed this to you a couple of weeks ago, but I just want to make sure you are all aware of this really nice little holiday countdown calendar that my friends at i7 have been putting together. So there's something to learn about Cilium or eBPF behind every door on that calendar. So I think that's a really nice thing. Okay, so with that and the headlines all done, I think it's time that we move to the main topic of today. And today, let me welcome Alan McGuire, who works at Oracle on eBPF and Linux kernel networking. So hi, Alan.
Hey, Liz. Good to talk to you.
Yeah, so Alan has been a friend of the eBPF community for a long time and has spoken at least a couple of times, I think, about or at the eBPF summit. And in September, Alan did a talk about bpftune. All the talks at eBPF summit, time is precious. There's not a lot of time. But Alan had made a comment about using reinforcement learning in bpftune. So we thought it would be a really good idea to have him come back and tell us a bit more about that, because that sounded pretty interesting. So welcome, and thanks for agreeing to tell us more about it. I think we should start by just talking a little bit about what bpftune is and introducing people to the general idea of it.
Absolutely. Yeah. I mean, bpftune is an attempt to solve a problem that we have seen in Oracle, and I'm sure other folks have run into too. And if I just pull up a console, you can kind of see what this problem is. So we have a lot of tunables on a system. I can keep going there. There's about 1,200. This is an upstream kernel on top of Oracle Linux. So there's an awful lot of stuff that you can choose to do in terms of tuning your system. That's kind of hard to manage. And particularly in our world where we have, we have a cloud, we have a lot of different systems running. A lot of the time, there's different answers for different types of systems. So the thought is there ways that we can actually come up with kind of algorithms and techniques to do this kind of stuff automatically? For some of these tunables, there's just no one right answer. But a lot of the time, what happens is that you can figure out a little bit about from the system what the right answer might be. And we were seeing the same tunable issues, particularly in the networking space, crop up for the same tunables again and again. And what would often happen is a bug would be filed, engineers with experience in that subsystem would post some suggested tweaks, and the problems would be resolved. But there's a little bit of time lag in terms of solving things that way. So the thought was, maybe BPF can do something here. It's one of those kind of problems where we've got this whole new bag of tricks. Is there another way we can approach this problem? So that's kind of the thought behind bpftune, I guess.
And maybe give us some examples of some of the particular tunables that you've been using bpftune to experiment with, just to give people sort of concrete examples of the kind of things that you can be tuning with these. I don't know what the word is, parameters.
Yeah, exactly. So, one of the main ones that cropped up in bug reports repeatedly was the TCP buffer sizing. So the TCP send and receive buffer sizing. So if people aren't familiar, this is basically what the maximum value you can tune your buffers to, your send and receive buffers to. So, when you're receiving traffic, let's say if you're, watching this live stream now, if your receive buffer is too small, you're not going to be able to, you're going to run into performance issues. So if you could automatically tune that based on the traffic patterns you see, that would be great. But here's the problem. If you make that buffer too big, then you can have, latency delays and stuff like that. So there's some sort of sweet spot to figure out in a problem like that. So that's where bpftune comes in. That's where BPF comes in as well, because we can compute a lot in kernel with BPF. We can, because we can inject code into the kernel, and we can share information with user space. So with all of those kind of pieces, we can start to, answer more complex questions about system state. So in the case of something like the buffer sizing, we can look at, okay, how big is the buffer? Are we at the point where we've hit that buffer sizing limit? And then we can make a decision to perhaps increase that buffer size. So we can send a message to user space using a BPF communication technology like a ring buffer. And then user space can make a decision whether it wants to bump up that tunable or not. But the power is then we can also ask the question, did that help or not? Because obviously, if you just keep bumping up a value forever, you're going to run into some of these issues with latency. So one of the things bpftune does is it looks at how we're changing the buffer size, and it correlates that with the round trip times that we see, so the latencies we see. So if we see that our bumping up of those buffer sizes is correlated with latencies, then we know that our tuning is doing something bad, and we want to back off from that. So it's putting all those pieces together.
Yeah. Brilliant. I think you mentioned that we could, as a demo, run bpftune while we're doing the stream and then see how it adapts.
Yeah, let's do that.
Parameters.
Let's do that. So, so I've got bpftune here. Let's just see. So we can see there, it's all on GitHub. We'll make it and we'll install it, and we'll start running it. And then what we'll do is we'll maybe come back in a couple of minutes and we'll see if it's done any tuning for us. Now, in a situation like this, our default tunable values, particularly for streaming and stuff like that, can sometimes be a little bit low. So we should probably see some tuning happen.
Great.
Okay, so now let's just see here. Are we up and running? Okay, we are. So we can see there's a bunch of, actually, let's just show you this, because there's a bunch of BPF programs running. So we can kind of, actually. So basically what's happening is each of the tuners has its own set of BPF programs that it uses. So here that's where we leave memory pressure. This is where we enter memory pressure. So that's the other thing that happens as well when we're bumping up some of these values. If you can imagine, if you have a big buffer for each TCP connection and then you get this sudden bomb of connections, you're going to run out of memory. So you want to see, if you're entering memory pressure, you then want to start ramping down buffer sizes as well. So the big thing about bpftune is you've got this push-pull between all these different constraints. And if you can find a good way to balance that based on the behavior of the system, then you get to a good place. So that's the real aim. Like, take what your system is really doing and assess how it's performing, and then tweak things based on whether things are going well or not.
That's making me kind of realize that there's more than one place where you might need to observe events in order to understand what the the impact of those tunables is at any given time. Is that, and that's why you have so many different TCP related programs running right now. Is that correct?
Yeah, exactly. So there's a lot of different places where we're observing things. There's a lot of different places where we're making changes to the system. So for the case, so each one, there's a BPF object. Actually, I can, maybe will I show you? That might be kind of a little bit easier. So we'll look at the bpftune code here. Now, this might be a bit small, but let's see here. So, and the other thing to say is each tuner has a manual page, and each tuner has a BPF object and associated user space side. So here's the BPF side of the connection tuner. Now you probably can't see this, but
yeah, can we make that a little bit bigger? It's a little bit small. I don't know if you can zoom in.
Yeah. How are we looking?
Looking better to me. Yeah.
Okay. So we can see there's a SOC ops program. So this is a TCP BPF program, which you take and you attach to a C group, and it runs for particular events in the lifetime of a TCP socket. So we use that to enable events like state changes. Actually, now I think of it, this is the congestion control tuner. I'm looking at the wrong one here. So we'll talk about that one later when we talk about reinforcement learning. TCP buffer tuner is the one we want. Okay. So here we go. So let's see. Yeah, so here's where we enter memory pressure. There's an F entry there. And that's actually a little wrapper function. So one of the challenges with bpftune is you got to run on a bunch of different kernels as well. So that wrapper will take that and turn it into a K probe for an older kernel as well. So there's if you run bpftune, actually, this is something I should have mentioned. So because support varies of what you can do on different kernels, it will use K probes and older kernels, and it will use F entry, which is the faster BPF trampoline based function entry on newer kernels. So you can run to figure out what's supported. You can run bpftune-S, and here we can see bpftune works fully. So we've got all the support we need because this is kind of an upstream kernel. And there's one of the other things that bpftune does is it works well in network namespaces, and network namespace cookies are a really good way to identify what namespace it is. So if you have that support, then we can do cleverer stuff in namespaces. So for example, we can have a particular TCP buffer tuning policy in one namespace and not in another. So it's namespace aware, but having the network namespace cookies really helps with that. So if we don't have that, there's sort of less we can do. So there's a sort of fall off in support as you get to older and older kernels, but we try and compensate where possible with things like K probes, if we're stuck.
Great. And that per namespace tunability will help in a containerized environment.
Exactly. I mean, there's a different answer for different environments, so sometimes you need. So this is sort of how the architecture looks. I thought it'd be no harm to show this. So the main bpftune service is on the left, and that's composed of a number of shared objects. And each of those is a particular tuning domain and has particular BPF programs on the kernel side. So each of these has baked into it BPF skeleton, which if folks are unfamiliar with that, it's a way of taking a BPF object and kind of creating a header file which has that object embedded in it, and it makes dealing with BPF objects much easier. In the past, you had to have a separate object which you'd have to load, and it could be a little bit cumbersome. So this object, it gives you this kind of a byte array which represents the BPF object you're interacting with, and it also gives you a bunch of APIs to interact with it. So it's really neat, and it makes that interaction much easier. And actually, if you're building BPF solutions into libraries, I found it's really nice because you just got to include that header file and you're off to the races. So that
Fantastic.
works well.
Good. All right. So I think we probably understand what bpftune is. And now, you made that comment about reinforcement learning back in September. I think we need to dig into that.
Exactly. I've got to pay my dues now. Let's see, get back to the presentation mode. So, so there's one tuner in bpftune, the connection tuner, which is using the reinforcement learning techniques to do TCP congestion control algorithm choice. Now, I should be clear that this is not in BPF. You can implement your own TCP congestion control algorithm as well via this struct ops method. This isn't that. This is choosing between a bunch of existing congestion control algorithms. So I just want to make clear that that's what this is doing. It's not its own congestion control algorithm. It's making a choice between the existing ones at a connection established time, and it's using reinforcement learning to inform that decision. Actually, just let me get this full screen again. Um, presentation mode, sorry. Okay, so reinforcement learning, to talk a bit about that, because a lot of the time people talk about machine learning these days, they're very focused on deep learning and neural networks, which is great, but this is another technique, and this is a much more action orientated technique. So it's a learning approach where we think about agents taking actions in environments and using reward signals from those environments, and trying to learn how to learn from their environment to figure out how it can maximize those reward signals over time. So think about a rat running a maze to get the piece of cheese, or things like that. And the aim is to learn over time from that environment through actions, which actions lead to rewards by exploring. So you want to explore your environment, and then at times you also want to exploit your environment, which is when you want to maximize those rewards. But there's an inherent tension between those two, because if there's a small reward in one place, in neural networks, we call this like a local minima. You might be tempted to always go for that small reward, but if you explored, there could be a bigger reward out there. So that exploration dilemma is always in place when we're talking about reinforcement learning.
So the rat in the maze might find a small piece of cheese and has to make a decision whether to go for the small piece of cheese or carry on exploring, looking for a bigger piece of cheese.
Yeah, exactly. And some reinforcement tasks are like that, so they're episodic. So like each run in the maze is one episode in reinforcement learning terms, and some are continuous, so they're happening all the time. So think about your Roomba running around the place trying to clean your house. So that's a continuous task, where something like a game of chess or running a maze is episodic. So the diagram here tries to explain that we're the agent, we're acting in the environment, we get we're in a particular state, and we take an action. Then we get as feedback from the environment a reward signal, perhaps nothing, perhaps actually a punishment as well. And then we get into a new state. So it's trying to basically map out the reward environment, figure out where rewards are, figure out which kind of behaviors lead to rewards, and which kind of behaviors to avoid. And it kind of fits with bpftune, because this is, if you remember, we were talking about it earlier, that it's this kind of model of acting, taking actions, tweaking tunables, and seeing the effects. So in this case, we're kind of thinking of the effects in terms of reward. And in particular, in this case, we're thinking about TCP congestion control. So the next step is kind of to figure out, well, okay, what's the reward in this context? Is there a way that we can kind of formalize that?
So what kind of rewards would we have? I mean, is that minimal latency, maximum throughput?
Exactly. Yeah. So we kind of build it. Well, I mean, actually, a lot of the stuff to do with this. Should we talk a little bit about what congestion control is first, or we just?
That's a good idea. Yeah, let's do that.
Yeah. So people probably remember when they've looked at TCP that we have sequence numbers and to transmit and acknowledge, because it's a reliable protocol. And the size of that window that we're using is negotiated between the two sides of the TCP connection. And sometimes one side can close its window because it can't receive anymore, and then it can open it up when it's ready to receive again. So, but that's all about the two ends of the connection. And what happened when folks are building the internet is they realized that we have this world where there's hundreds and thousands and now millions and billions of TCP connections, all kind of landing on particular intermediate systems. So we have to start thinking about other aspects of the connection. So the analogy I draw in this is the sliding window stuff is great, but that's sort of like going for a drive and thinking about, at the end of my drive, there's a parking space to park in. Like, that's good to know, but you also want to know if you're going to hit any traffic along the way. So that's where congestion comes in. So TCP sometimes has to be not transmitting to the fullest that it's able to, based on its observing congestion in the past. Because the internet got very close to something called congestion collapse, which is where we got to the point where, because of the way TCP reacts to congestion events as well, it will retransmit, and then you get into this kind of cycle where congestion gets worse. So you really need to be able to detect and respond to congestion in protocols like TCP. So that's kind of key. So that's where congestion control algorithms come in. They try and use signals to try and figure out, how should I limit my TCP transmission?
I'm now wondering how close we got to congestion collapse, but yeah, that's probably a question for another day.
Yeah, absolutely. So coming back to the reinforcement learning then, I mean, maybe it would be good to sort of talk about the terminology and kind of relate it to TCP connections. So in our terminology, we talked about episodic tasks like running a maze or whatever. So our TCP connection lifetime is our episode in this particular case. And our action in this case is to choose a congestion control algorithm. And at the end of our connection, at the end of our episode, which is our connection lifetime, the idea is we're going to use information about how that connection performed to try and figure out a reward signal. So that's the idea. And the other thing, and this comes back to this sort of exploration, exploitation thing as well, is we can't be just greedy and sort of go for the best algorithm, best performing algorithm so far, because network conditions can change, and perhaps maybe 1 minute data center TCP is working well, next minute BBR might be. So we need to have some way of trying other congestion control algorithms, even when we think we found a good one for the particular circumstance. So one of the ways that reinforcement learning suggests is to have this kind of epsilon greedy approach, which is basically like you pick the action which gives you the highest reward most of the time, but from time to time you also select a random action. So that's a way of balancing a little bit of exploration with exploitation. So you're exploiting your reward signal most of the time, but from time to time you'll try something new to just see if there's any extra rewards out there for you.
That makes sense. Yeah.
So when we're doing all this stuff, the idea is we're collecting information on a per remote host basis, because, you know, we're trying to think about the network path between two systems. So as we're learning, we're going to learn about, you know, connection information for a remote host. And as we have multiple connections to that remote host, we're going to learn by trying different congestion control algorithms, which one's working well. And the idea is for a particular remote host, we want to figure out a good answer. So we're collecting information on a per remote host basis. So that's kind of the rough idea behind how we're applying some of this stuff. And then in terms of the actual signal, well, I suppose maybe we should talk about how you do this in BPF as well, because obviously it's trickier to do some of this stuff in an environment like BPF where you are constrained in what you can do. So, you know, we talked about the BPF SOC ops programs earlier on. So they kind of allow us to attach to a particular C group and, you know, run BPF programs at various points in their lifetime of the TCP socket. So in this case, we want to run our program at the connector accept time, and then at that point we want to choose our congestion control algorithm. And then when we want to, when the connection closes, we can use a state change to look at when the connection closes to then assess how we did. So they're the two kind of BPF triggers that we're using in this particular circumstance. And BPF provides all the stuff we need, which is great. So it provides those hooks. It also provides a way to use a BPF set sock op. So this is where you can actually set socket options in a BPF context. So you can choose your congestion control algorithm in BPF at connection setup time. So the algorithm selection needs to happen in BPF context. And that also means that we need to make decisions. Remember, I talked earlier about this kind of epsilon greedy approach where we choose the algorithm with the highest metric most of the time, but we also might sometimes want to pick a random congestion control algorithm too, just to keep that exploration window open a little bit. So BPF is a random number helper as well, so we can use that to pick a random state. So we've got all the stuff that we need. The only downside is that we only have integer division because we're effectively in the kernel, so metrics need to be simple enough to take that into account.
Okay, go ahead, talk about the rewards.
So yeah, I mean, with BBR, the BBR paper is kind of a good read. So I'd suggest take a look at that. And what it basically says is that you want to get to the point where your connection is filling the communication pipe, what they call the bottleneck bandwidth. And basically that bottleneck bandwidth is the bandwidth of whatever the choke point is along your channel of communication. So if you think about it as literally, as Al Gore would call it, a sequence of pipes, it's the narrowest pipe in your connection. So that's what's limiting your connection. And you really want to tune to that if you can. So if you're operating at that point, you're filling the communication pipe as much as possible without overfilling it, which leads to congestion. So what we want to do, the signals we want to gather from a TCP connection are the minimum round trip time that we've seen, because that gives us a good sense of what the actual latency can theoretically be. We might not always hit that, but if we know what the minimum is, we kind of know roughly what the latency is. And then if we want to estimate that bottleneck bandwidth, we want to look at the maximum packet delivery rate we see as well. So it's kind of like the fastest round trip time we see and the best packet delivery rate we see. So they're what BBR uses, but we can also use them to compare across our different congestion control algorithms and build a reward signal out of them. So that's really how we kind of build our metrics. So we want a good algorithm that will approach the minimum round trip time, so as fast as possible, and then the maximum packet delivery rate as well, highest throughput as possible. So it's
Right, and that's
balancing.
during that lifetime, that episode being the duration of that TCP connection.
Yeah, it's basically when you're on the way out the door and you're closing the connection, you want to say, okay, how did I do? Did I, what was my minimum round trip time observed? What was the maximum packet delivery rate? And how does that compare? And this is the key thing. We're comparing it to the best we've seen across all the congestion control algorithms that we've used. So, the idea is it's kind of like an error signal compared to that. And if we did better than the best we've seen, then we want to basically take a chunk of whatever that difference is and add that to the value that we place on that congestion control algorithm. So it's a little bit like when we talk about the, in neural networks where we want to adjust a weight, we take the difference between whatever we wanted to get and what we did get, and we use a learning rate to kind of take a chunk of that to try and tweak things to get a little bit closer to the right answer in the future. So that's kind of the idea here as well, except we're using rewards rather than, precise error signals.
Right, yeah. And I guess if we're choosing between different algorithms, they're kind of discrete choices. So we're kind of, I guess we're ranking those different choices according to these metrics that we see when we use those different choices.
Yeah, and actually, I'll get into this a little bit later on. What's interesting is even though we're using pretty similar metric to what the BBR does, sometimes we don't use BBR, which would kind of suggest we're getting to the heart of, hopefully we're getting to the heart of, a good evaluation of these various algorithms, because we're actually seeing, how do these things perform. And it's even though it probably does, because it is quite similar to BBR, because BBR essentially is trying to build a model of the connection rather than a lot of other congestion control algorithms use loss as a signal. So a lot of them operate in different ways. But what I've seen in practice when running this is that, we choose different algorithms based on different network conditions. So the default algorithm, which is cubic on Linux, actually runs pretty well most of the time. It's when you start to run into loss and latency that sometimes other algorithms might be a better choice. And that's really, that speaks to the dynamism that something like bpftune has, that sometimes you need to react to what you're seeing on the particular system and kind of learn from that. So that's kind of the idea.
So yeah, my next question was going to be what kind of results you've seen. So I guess you need to compare it to what happens without bpftune and how it compares when you introduce bpftune.
Exactly. So to kind of get a sense for this, and you can run some of these tests as well. I should mention that the bpftune repo has a test suite as well. So some of the tests are things like, set one of the tunables to a really low value, like let's say the TCP buffer size, and make sure that it ramps it up when you run traffic. So there's a bunch of different tests for various things. There's some eBPF tests around the TCP connection tuner, which is doing this reinforcement learning based tuning. So this is where some of these results come from. So if folks want to try and run that themselves, they can too. So we're trying to simulate networks. So we're running everything within the same system using network namespaces. And we use something very handy called, I don't know if folks have used it before, the NetM QDisk. So net emulator, I think is probably what it stands for. So this QDisk allows you to induce latency and loss conditions on your connection. So you can kind of simulate situations where like you have a 100 millisecond latency or whatever, even though you're running locally on the system. So by default, things are very fast. So the idea is
whether it introduces that using BPF or not.
Sorry?
I'm wondering whether it introduces those delays using BPF.
I think it was actually slightly before BPF, but I mean, it's the sort of thing that BPF could give you a fully programmable version of that, which would be kind of nice. I mean, you're kind of, yeah. I think with this, it's very, very nice. It's very flexible, but I suppose it is a little bit more hard coded that it gives you a certain set of options. But yeah, I mean, again, like so many things in the kernel, BPF can provide value in that space, I suspect.
Yeah. Interesting project idea out there if you're watching and thinking, what could I do?
Exactly. So the idea here is basically we want to run a bunch of eBPF sessions between the client and the server. And we want to run bpftune. As a baseline, we want to not run bpftune. We want to see how eBPF performance holds up under various network circumstances. So we're going to do things like just do the default, no tweaks to latency or loss, and kind of see what the performance characteristics are. Then we're going to start introducing loss and latency and just see how the algorithm performs. So when we look at some of these results, I hate to do this death by PowerPoint thing with all these tables. But the thing to kind of watch for is how quickly do these reinforcement learning algorithms converge? Because that's one of the real sells, I think, of technology. I mean, one of the big selling points for me for reinforcement learning is it's quite simple. You can implement it in BPF, so it's not overly complex to do, and you can take a look at some of the code in bpftune to kind of see how some of that was done. But it converges pretty fast, which is something which you would really want, because it may well be the case you don't actually have that many connections to a remote system, so you don't get that many opportunities to learn the connection path characteristics. So you want something that's going to be a quick study and figure out exactly what the right thing to do is. So when we look at some of these results, we're going to look at, for the various congestion control algorithms, we're going to see, okay, well, did bpftune try out all the different options? How many times did each one run? What kind of metrics were calculated for each one? Did they always make greedy choices? So the idea with the greedy choice, if you remember, is pick the best one. But we don't want to always do that, as we mentioned, because you sometimes want to pick a suboptimal algorithm, because sometimes it might actually start to do better. So we won't always see the number of greedy times that a particular algorithm was chosen match the amount of times it was chosen. So we're sometimes doing that random choice. So when we look at the loss rate of 0, there's a small overhead there we can see. So when we're looking at the results sender in bold and the results receiver, we can kind of see that the baseline is slightly faster, and we are attaching a bunch of BPF programs here. And one of the aims more long-term is to get some more trace points into the kernel, because we're attaching in a couple of places to functions. And anyone who's done that kind of business with the Linux kernel knows you sometimes don't have a function exactly where you want one. That can be a bit of a pain. And this is where trace points are great, because a trace point can be in the middle of a function where you actually have access to all the fields that you want. Whereas sometimes at a function boundary, you just don't have the information you want. So sometimes you have to figure that information out when you attach to that function. And then sometimes that function runs too many times. Like if your trace point's deeply embedded in a function and it's kind of conditionalized such that it only gets run like 10% of the time, then there's obviously much less overhead in running that. Whereas if that function gets run a million times a second, you're in big trouble. So one of the big things I should mention about bpftune is we try to aim not to attach to functions that run very, very frequently. That's a real killer for performance. But in the long term, there are a couple of places in the TCP stack where it would be nice to get a couple more trace points, perhaps. So that's one of the kind of things that I hope to come out of this work as well, that we can upstream some trace points into some choice places.
Yeah. So talk us through some of these, the results that we're seeing here for the choice of different algorithms, and what does metric mean? Is that some kind of combination of the late, there was the minimum round trip time and
the packet, the packet rate. So it's a combination of the two. So the number itself is pretty meaningless, but the lower number is better, because the lower number is basically closer to the error effectively between the ideal values for them, the ideal range, the minimum round trip time observed, and the maximum packet delivery rate is lowest. So when you see a small number here, that's the winner. So we can see data center TCP won in this particular case. And this is where we have no loss induced on the connection. So you can see, if you look at the chosen column there, that tells us how many times out of 75 odd connections we chose data center TCP. So we chose it 65 times. In this case, we chose it greedily all of those times, but we chose some of the other algorithms as well. So we used cubic twice. One time that wasn't the greedy choice, which means we chose cubic when it wasn't the most optimal choice that we had at the time. Similarly for BBR, we chose it 3 times. Twice it was the optimal choice, but once it wasn't. So this is kind of all in kind of reflective of the fact that as we're kind of exploring these different algorithms, we're learning a little bit about the characteristics, and we kind of don't come back to them once we realize they're not doing well. But we can come back to them like once or twice. So you can kind of see that the greedy column is sometimes different to the actual amount of times it was chosen. So and HTCP was chosen 5 times, and that was only chosen greedily once. So this is random, so you're not going to see a uniform distribution here. But we see 65 times out of the 75 odd, we've chosen what is showing the minimum round trip time, which is 4 microseconds, I think, and the maximum delivery rate. So it chose the right answer here effectively. This was the most effective algorithm in terms of round trip time and delivery rate. So we didn't get anything out of this because there was a small overhead in running the BPF programs. But when we start to look at some of the cases with loss and latency, we'll see that there's some benefits to figuring all this stuff out. So, and that's just to underline as well, this is a case where even though we're using these metrics, which kind of do fit quite closely with what the BBR paper talks about, we didn't choose BBR in this case. So that would give you a bit more confidence that we're kind of exploring to find the best answer.
And that isn't a reflection on the algorithm, it's a reflection on the circumstances, or it might be a reflection on the algorithm, but it probably is also a combination of the network characteristics that you were using at the time.
Exactly. So we're kind of standing outside all these algorithms and using the same metric to look at all of them and kind of saying, okay, who's the winner? That's sort of the philosophy. So
who's the winner to connect between here and there today? Yeah,
exactly. And that's today is the big thing, because, you know, as we said, this is what they call in reinforcement learning a non-stationary problem, that these things can change. And that's where that kind of epsilon greedy approach, where we always try new things, is really important, because we need to just double check that we've got the right answer. We don't want to converge too closely. Now, you can sometimes pay a price for that. So, you know, there is that risk that you're going to pick an algorithm and it's going to perform really badly. But if we're committed in the long term to trying to find the best answer, sometimes you do have to try things which may be suboptimal, because that's just the risk you got to take, I guess.
Yeah. I think it's one of those things that you realize as things scale, things have to be done a little bit more almost on a statistical basis, rather than, you know, because it's things like, you know, if you have enough servers running, one of them is going to crash because hardware has a finite life. And if you use enough different physical internet connections, one of them is going to, you know, somebody's going to come up and dig the road in the wrong place. So things are going to go wrong, right?
Absolutely.
All right. So talk us through so this is looking to optimize something different, is it? And on the loss rate?
Well, this is all the same stuff, but basically we've induced a loss rate of 5% on the connection. So remember we talked about that NetM Q disk. So we basically told that to drop 5% of the traffic. So we want to see in conditions of loss, which is something that some congestion control algorithms use as a very strong signal to back off. We want to see how things are going to perform. Are we going to pick the optimal choice? Because again, we're trying to have this objective metric that stands outside all of these algorithms. So we want to make sure that that metric works in situations where we're losing packets, and also situations where there's latency in the connection. So in this particular case, we actually converged to BBR. You can see we chose that 62 times. And we actually see a big bump in performance. So we see a 2x. We're seeing, you know, 1100 megabits per second, where we're only seeing 500 before in the baseline. So choosing BBR has been a good choice in this circumstance. And again, we can see we chose it 62 times. So the vast majority of the time we've stuck with that decision, although we've tried to use the kind of non-greedy choices a couple of times. And in this case, data center TCP, it had nearly the same round trip time. It's slightly longer. You can see it's 4 there versus the 3 we have for BBR. But the big thing is the delivery rate. BBR just massively outpaces the rest. And this comes back to how that algorithm works, that it doesn't use loss as a signal. It tries to model the connection characteristics. So a lot of the other congestion control algorithms are kind of pessimistic. Once they see loss, they think, okay, we're snookered. Whereas BBR tries to be a bit more, tries to build a model, I guess, a bit more of the connection. So it's doing better. It's not dropping the actual congestion limit down as strongly, and we're seeing that in the delivery rate here.
Super interesting illustration of how, you can't, the algorithm that you want depends on the circumstances. Yeah.
And again, I think that the real key thing here is the fast convergence too, because for a lot of learning algorithms, I mean, even for deep learning, a lot of the time, it takes a long time to converge. And they have all these complicated techniques like this batch learning thing, where you take all your training data and you have to chop it up into batches. But we're learning on the job here, which is a lot harder in a certain sense. So you need to learn fast, because as I said, that exploration, you do sometimes pay a penalty for that. But if you're not paying that penalty very often, and we can see here, it's like 90% of the time we're actually choosing the optimal choice anyway, then it's worthwhile. But I mean, in this situation where you have to learn on the job, you really want it to converge quickly. Otherwise, there's no point in doing it. And again, because we're dealing with particular remote systems, you may not even have that many episodes to learn from, not many connections to learn from. So you want to make the most of the information you have, and we can kind of
Totally
see.
makes sense. Yeah. So have you got another? Okay, even higher loss rate. Yeah.
Yeah. So things really start to fall apart with a 10% loss rate in normal circumstances. But again, BBR to the rescue in this particular case. So you can see here that we've had a high maximum delivery rate compared to the others. It's kind of I suppose like what 3 times the cubic, which is the next best. One of the things you should note here as well, which is true, is the cubic, which is the default for Linux, works pretty well in most circumstances. But when you start to get into loss rates and latencies, sometimes the other algorithms do outpace it. So this is why making a choice sometimes is a useful thing to do. So we're seeing a sort of nearly 10x improvement in performance here by making the choice and choosing BBR. We can see particularly the latencies, the minimum round trip times are all roughly similar, except HTTP is a bit of an outlier there. But the maximum delivery rate's the real thing that distinguishes BBR in this particular case. So we're seeing that's much higher, and as a consequence, we get a much better result. And then when we start introducing latencies, I won't belabor these anymore, but we can see with a 10 millisecond latency, we end up getting a decent performance as well, the kind of 5x performance. Again, we can see like 60 times we chose BBR, which is working well in this case. The round trip times again are roughly similar, but BBR is slightly faster, and the delivery rate there is pretty high compared to the others. It's sort of twice the other ones. So again, we can just see
just based on that 0 for the maximum throughput for cubic, it looks like cubic couldn't cope in these circumstances.
Yeah, no, that might be an artifact of one of the algorithms, the way they work. If you've only had 1 or 2 samples, sometimes you don't get a great number. I think that could actually be symptomatic of a bug. So I want to be careful not to overinterpret that. You shouldn't really be seeing zeros there. I think that's probably. One of the problems is we have to kind of round things, and when we're dealing, comes back to this whole idea of having to do integer-based calculations, and we can't use floating point numbers in the kernel. So sometimes things go a little bit awry with that. So that could be an artifact of that. I must take a closer look at that one, actually. Thanks.
That makes sense. Yeah. And also it makes sense that the round trip time has got considerably longer now that we have introduced latency.
Exactly. And we're kind of seeing that it paced with that. And then in this case, we see a similar thing that we've chosen BBR, the round trip time. Actually, in this case, the minimum round trip time isn't the best one, but the delivery rate is so good that it's one for those reasons. And we can see that the metric there is much lower compared to the other. So that metric is that combination of those 2 values that we use to decide. So hopefully the picture emerges that we're doing a decent job of finding the better performing congestion control algorithms across various conditions of loss and latency. And the idea of using reinforcement learning is valuable, I think, here, because it shows we're converging pretty fast, which is important, and we're getting different responses for different network conditions. And that's sort of what we want to see in something like bpftune, that we're learning from the environment and we're learning quickly. And that's the real key, because you don't want to pay the tax for the first day or so of your system running, it's creaking and trying to figure out what's going on. You want to get those answers pretty quickly and then be able to benefit from them. So we're kind of seeing some of that here. So it seems to work reasonably well. So there's more work to do, of course, but it's probably, one of my experience from this is that because reinforcement learning is relatively easy to implement and simple in a BPF, simple enough that it can be implemented in a BPF environment, it's a useful thing to have in your toolbox, I think.
So before I ask my next question, I just want to remind folks who are watching, if you have got a question, then type it in and we will try and get to it. I'm also just going to bring up a couple of comments. So Martin had said it's a very nice use case of these technologies. And earlier on, when you were showing some code, Lacoste, so there was great details and tips on eBPF programming. So thank you for those comments. As I say, do type in if you've got any questions. Now, my question is, you've mentioned that you can do the reinforcement learning within the BPF programs. Can you also set the tunable from there, or is that where the user space part of the BPF comes?
Well, you can actually do either, and some tuners will actually. Let me see if I can show you that actually. So some tuners will send events to user space. So actually, sorry, let's bounce around here a little bit. I'll show you the, so if we look at the sort of diagram of how things work. So in some cases, what we do is all of the BPF programs, when the tuners are loaded, they all attach to a shared BPF ring buffer for events. So this allows tuners to send events to their user space counterparts. So we can see in this case the BPF program. So in this case, our send buff expand has fired. So that's when TCP is expanding the send buffer size. And so we send an event telling user space that via the shared ring buffer. bpftune then gets it and looks at the tuner ID and sends it to the right tuner user space, and it calls an event handling function there, and that can make a decision. But actually, in the case of the TCP congestion tuner or the TCP con tuner, it actually does that in kernel as well. So there's been some great work adding the ability to set to call set sock opt within BPF programs. It's really, really handy. And let's see if I can find it here. So in this case, so this is basically where we're connecting either active, it's an active connection where we've done a connect, or a passive established connection where we've accepted a connection. And in this case, we're enabling some flags for additional events. In this particular case, we want to see state change events, because if you remember, what we want to do is when the state gets to the closing TCP state, we want to look at our connection and kind of figure out, okay, well, how did this connection perform? So that's what's going on. But then down here, we can see we're looking here, we're looking at our metrics. We're looking through our states for the right metric, for basically the one with the minimum metric. And if there's multiple metrics which have minimal values, we randomly choose one, in the same way as we do the epsilon greedy as well. Sometimes if we want to choose one at random, if we decided to do that. So you can see there we're choosing a random algorithm 5% of the time. Then here's where we set our congestion control algorithm. See if I can click on that. So yeah, so we're calling BPF set sock opt here with the appropriate congestion control algorithm. So we're doing that just as the connection gets set up, and then it's going to use that congestion control algorithm for the rest of its lifetime. And then when we get to that connection closing, we can see how it did, and then we can update our metrics based on that. So that's kind of the flow in this case. So it's really nice because we can do pretty much everything in BPF. And we don't need to do a huge amount of user space. Whereas with some other tuners, we need the kind of cooperation between the two.
That makes sense. Great. So I wonder if now would be a good time to take a look at the results that we've seen during this stream.
Yeah, let's see. Actually, be interesting to see. Now, hopefully it's done something. So basically, when I booted up my computer about 2 hours ago, so we've started off with what are the default tunable settings. So we should see. Okay. So we had some congestion control stuff going on earlier. We had some increases in buffer size for TCP RMM. So this is basically the receive buffer size thing we were talking about. We increased the maximum buffer size because we're streaming effectively, and we need a bigger buffer from what the default is. I found that I run bpftune on my laptop every day, and I found that over time that's the big one. So if you're on YouTube, if you're watching, if you're watching the playback of this or whatever, you're gonna need a bigger receive buffer size to be effective. But the key thing is we're actually balancing that with looking at the round trip time as well. So if we get that buffer to a point where it's too big and we're seeing latencies, which are increases in round trip time, we back off. So it's always that balancing things going on, that we can't just blindly increase a value constantly. Because then if that's what you just tune the value to the maximum and then you're done. So obviously that's a way too simplistic approach, because there's always trade-offs between these tunables. And bpftune, the aim with bpftune is to try and explore how those trade-offs work, because we often think there's this, I don't know if anybody's seen any of these presentations from the Rust community, but there's one where they talk about this idea of bending the curve. And the idea is, when we think about trade-offs in software, we kind of think of it as a zero-sum game where you improve one thing and you disimprove another. So if you improve round trip time, you're gonna mess with throughput or whatever. There's a constant push and pull between them. But in reality, it's kind of a little bit more complicated than that. And the idea of something like bpftune is we want to empirically explore what the relationship between these variables really is in practice on the system in question, because we don't know for sure that that's exactly how things are going to behave. I mean, there's theoretical ideas about how things behave, but you know, every system is its own particular snowflake, and we need to figure out exactly, you know, what the characteristics of that snowflake are. So having a programmatic method to do that seems like a good direction.
And I suppose another potential thing that you could introduce is the idea of being able to tune to optimize for different use cases. So, for example, if you're watching YouTube, it doesn't matter quite so much if there's a bit of latency compared to if you're on a Zoom call and you do actually want to be able to have a conversation. You know, it's latency that can create that sort of weird gap between people. You know, like when in the old days when we used to speak on phone calls that went via satellites, and you could sort of, things were odd when you would try to have a conversation over a satellite call.
Yeah.
And I guess like, you know, latency is more important in certain circumstances. You know, maybe loss is really important in other circumstances. So, yeah.
And that sort of TuneD is very good about this, that you can use a profile based on, you know, what your needs are. But with bpftune, I kind of wanted to start from scratch. And actually part of the philosophy of doing this is not to always, you know, not to say that bpftune needs to be bpftune forever. It could be plugged into another tuning framework, and it's actually kind of architected like that. It's architected with a library and stuff. So the daemon is like just 100 lines of code, which calls into the library. So, but the idea with bpftune is, how far can we push the idea of, you know, you're starting from zero and you know nothing about this system? How much can you learn? And the hope is that because we have all of these new observability technologies with BPF, and we can do all this stuff at really low overhead, we can learn a lot about the system, and we can make some of those tuning decisions without understanding necessarily the user's intent for that system. You know, maybe we can go a certain way down that road. I mean, you may hit a wall with that eventually, but as a kind of thought experiment, as a sort of an approach, I think it's interesting to explore how far can we get knowing nothing about what the user wants to do with the system. And this is what the OS has to do itself. And frankly, that's why we've ended up with so many tunables, because it's really hard to do. It's really hard to know what the right answer is in general. But, you know, maybe having sort of tunable auto-tuning mechanisms like this can compensate a little bit for that. So that's the aim, at least.
We have a question from Martin. Is there already a ready-to-use integration for a Kubernetes cluster running with Cilium?
No. I to be honest, I'm not great with the container world, so I have to admit ignorance with that.
I'm going to speculate the answer is yes and no, right? Because I think there isn't anything. I doubt there's anything kind of specific for Kubernetes, and why would there need to be specifically for Cilium? But I suspect that if you just ran bpftune on the host machine, it would be tuning for individual network namespaces regardless. I don't know quite how it would interact with Cilium, so that might be an interesting question mark. But it seems to me like it might just work. Maybe exercise for the viewer, try it out.
Well, I'd be interested to see, you know, and if you run into issues, please feel free to file them. And one thing I should say is we're kind of maintaining within the project a kind of future plans section, you know, work, and it talks about work we've done so far, work we've got planned. So if folks can see, you know, areas we can go, things we should be tuning that we're not today, I'd encourage them to look at that. But yeah, what you say is true. I mean, the sort of vision for how this thing is to be run in general is for it to be run in the global namespace, and then because it's namespace aware, it can tune on a per namespace basis too. But the idea is sort of to sit outside of individual namespaces and kind of make tuning decisions for those namespaces. Now that may not always work for folks. Folks may want to not have it running for particular namespaces, so there may be things that need to be done in the future. But the design at the moment is that it has different tunable. It's doing different tuning operations in the global namespace than it is in individual namespaces. So for example, if I run an iPerf between the global namespace and the network namespace, which I've set up, and I've got an iPerf server running in that network namespace, it will do its tuning thing separately in the namespace than it is in the global namespace as well. But with the same goal to try and maximize throughput, minimize latency, all that kind of stuff.
And if folks want to try it out, they can find it on GitHub. The link is in the show notes, which is on HackMD. What kind of feedback have you already had from other folks who've tried it out?
Well, I think one of the things that's become clear is that it's quite difficult to run some of this stuff across multiple kernel versions. I mean, that's really the challenge. I think anybody who's maintaining a BPF project is probably seen aspects of this, that if you're attaching to specific kernel functions, if you're attaching to if you're using particular kernel data structures, things change, and change is a good thing, but it's sometimes hard to manage. And because certain BPF features are available in certain kernels, so there's been a little bit of work that we've had to do to try and make things work in different environments. So if you remember, I ran that support. Oh, hang on. Gotta run that as. So we can kind of see from that, what bpftune support there is. So the idea of having that support level check is that it tells you up front if your kernel is way too old. So anything below like the 5.6 kernel is probably a little bit old, unfortunately. Our 5.4 kernel, UEK6, will actually work because we backported some BPF features that are needed, like the BPF ring buffer. But for an upstream kernel that doesn't have BPF ring buffer, it probably is a bit old. But one of the things that we discovered is you have to work around this, and you have to do your best. So in some cases, we use F entry programs where we can for function entry, which are fast, but then we fall back to using K probes if that's not available. So you just have to kind of work with the system you have. But one of the things that's really valuable is having BTF. And if you don't have that, it's very difficult, because that BPF type format information allows you to do that compile once, run everywhere thing. So when you're accessing kernel data structures, you get the right offsets if you're running across different kernels, and that's really key. That's a real powerful feature. So it's important to have that. I think that's kind of a minimum requirement, really.
Yeah, I think compile once, run everywhere is a huge step forward for the ability to deliver BPF programs to other people without knowing what the kernel version is that they're going to have. So yeah, huge kudos to the folks who worked on that. Yeah. Fantastic. So, I mean, we're coming up to the top of the hour. I just wonder if there's anything else that you wanted to share about bpftune before we wrap up.
So let me just get back. Well, to the future work. I mean, one of the things we want to do is cover more tunables. We've mostly focused on networking space at this point, but we're interested in looking in other areas. We want to do some more benchmarking to look at more realistic production workloads, because obviously iPerf sessions are great for assessing network performance, but you want to test more complicated environments as well. We want to look at minimizing the overheads. As we saw, there is a little bit of overhead there, and part of that might be upstreaming some trace points, and also asking other questions about maybe there's other interactions with upstream that we can do around tunables. One thing would be maybe at the point that upstream uses at the point where a kernel uses a tunable, would that be a place where we could actually have a BPF hook that could make an assessment using BPF rather than actually using a fixed number? Because what bpftune at the moment does is it tweaks those numbers. So the kernel then sees the tweaked number and makes a decision based on that. But you could imagine cutting out the middleman and attaching the BPF program to the actual tuning decision itself. That might be an interesting direction in the future as well. Another thing we want to look at as well is that sometimes things just don't work. So that reinforcement learning stuff, what I've seen in most cases, it works well, but sometimes it might not work too well. So maybe we need multiple strategies for a particular tuner, and we want to switch between them based on metrics that we see. So if a strategy isn't working, we might fall back to something maybe more declarative. And we're keeping a feature plan for all this stuff in the Git repo. So if there's folks want to see, I'd encourage them to send pull requests or file issues about functionality they'd like added as well.
Very nice. And we got a nice comment from Lacoste saying, interesting insight on the kernel dependencies. So thank you for that comment. And thank you for everyone who's joined us today. Thank you so much, Alan, for joining us and fulfilling your promise to talk to us about the reinforcement learning aspects of bpftune. Really appreciate that. And hopefully we will hear more about how bpftune develops in the future. So thanks everyone for joining us. Wishing you all wonderful holidays, and we will see you in the new year.